Okay, I hope you guys can hear me. Sorry, today I cannot really teach during the lecture time frame just because I have to drive. Apologize for that, but nevertheless, I hope you can watch this lecture uh, today or during the lecture time or later in the evening. And fortunately, you cannot ask questions, but other than that, I hope it's about the same. And I'll try to go a little faster just to make sure that since first of all, I cannot really interact with you guys and cannot really ask any questions and stuff like that. So I probably can go just a bit a little. Man, we'll go a little faster. But anyway, so the point today we're gonna talk about the possibility of bringing isolation into the monolithic kernel. So for the last couple of weeks, we talked about isolation as a mechanism to improve security in the kernel. And specifically for the last week, we actually discussed in details different isolation mechanisms and which exist in modern CPUs. The question is, can we really benefit from those mechanisms by taking an existing monolithic kernel like Linux kernel, which is developed as a single file, not just a single file, as a single address space, where any variables can be accessed from literally from any other part of the system, and somehow introduce isolation with a goal to prevent exploitation of this kernel. So let's take a look. So again, just to make sure that we remember that motivation is for this isolation work is the same. So essentially, modern kernels are extremely complex. They're like in the tens of millions of lines of code, right? And they're running like dozens of individual subsystems like CPU scheduling, device drivers, memory subsystem. Most of those subsystems are familiar to us, right? And of course, like it's not surprising that like since the kernel is moving reasonably fast, and typically a kernel features something like 80,000 commits a year, the bugs and vulnerabilities are routinely introduced into the system. So if we take a look at the plot, which shows the vulnerabilities in the Linux kernel by year, right? So in 2009, like roughly 15 years ago, we were at around 100 vulnerabilities each year. There were some spikes, like 400 vulnerabilities in 2017, slightly lower numbers in 2022 and 23, but I kind of say that there is another spike here today in 2024. I don't have a number for you, but I looked myself, and it's in 400 vulnerabilities up to date. So again, so it's very easy to make a mistake, and we talked about it. Remember, we had a lecture on discussing what these vulnerabilities are. But roughly speaking, here is just a reminder. This is a very simple vulnerability which existed in Linux kernel from June 2011 to March 2019. So essentially from kernel version 3.0 to 3.13.6. And it's very, very simple human mistakes, essentially. Here, there are two variables. One declares the data structure itself on a stack, and another one is a pointer to that data structure. And here, this function, skb header pointer, should take a pointer to the data structure to a pointer to this one, but the developer accidentally sends a pointer to the pointer, right? And that's incorrect, which results to a stack smash attack. And this is correct. And you kind of know that stack smashing attacks are not that powerful anymore because we have stack canaries, have information flow control, stuff like that, shadow stack. But nevertheless, I'm pretty sure that this is exploitable if you very carefully start thinking about it. Another interesting observation is that a fair fraction of vulnerabilities or CVEs exist in the device driver subsystem in a kernel. So for example, 2017, out of like roughly 400 something vulnerabilities, 378 were in the kernel, but 71 were in the drivers, so essentially in different device drivers. And the tendency goes up and down. So one can say that maybe there is not a very strong correlation between the number of vulnerabilities in the main kernel and the driver subsystems or other extensions, but maybe there is, right? And the reason I'm bringing up this plot is that device drivers are kind of like a natural candidate for being isolated within the kernel, because if the kernel itself is really like well connected, device drivers are implemented as loadable kernel modules. And you can kind of imagine that if you have a technology, you will be able to essentially run the device drivers in isolation, right, from the rest of the kernel. In a typical kernel exploit, as it comes today, so attacker finds a vulnerability, let's assume in TCP stack in this picture, then essentially the goal is to gain some kind of a persistence, essentially make sure that the exploit will control, the attacker will control the machine after the reboot, and maybe even installing something like a rootkit, like a tiny hypervisor, which will virtualize the address space of the system in such a manner that the antivirus detection tools will not detect like a presence of yet another process running in a system. And that's the process which is controlled by the attacker, or not like it will not be able to detect the fact that the exploit is present in the system, right? So okay, so I keep kind of claiming that in this monolithic kernel, despite the fact that we deploy all sorts of protections like shadow stacks, kernel address space layout randomization, essentially the kernel executable code is not writable, and even like control flow, there's still attacks which allow the attacker to control, largely take over the machine as long as he or she has an instance of an exploit in a single monolithic system. And my claim, which I'm making here, that it's highly unlikely that it's going to change. I mean, it's nice, we have nice fuzzing tools which find more and more vulnerabilities, but nevertheless, I kind of say that a fair fraction of vulnerabilities is still added to the kernel. And if you stare at the kernel code, like if you really look at it with the goal to see that whether it's correct or not, you will find yourself quite a bit surprised that it feels like almost every bit of kernel is exploitable. Like maybe it's correct, and maybe by some kind of lucky coincidence or like very careful development process, the specific line is correct, but it's not guaranteed that it will be correct tomorrow because the kernel is moving slightly, the interfaces are changing, or maybe the locking discipline like changes from one version to another, or just even like that you didn't think about the problem in a specific way, and really you can think of how this specific couple of lines of code can be abused, right? So it's very, very hard to convince yourself that this unsafe system, like a system which is developed with an unsafe programming language like C, sometimes even assembly, can be done right. And of course, the natural question is whether you can improve security of those systems, right? And you might ask a question, okay, cool. So clearly there might be some ways to make them better. So in the past, people tried to say, look, we can probably formally verify, or in other words, construct a mathematical proof of correctness of a system through some kind of a formal verification technique. And that's true, that's possible. And like today we see tremendous advances in formal verification. It becomes easier and easier to do things. But yet again, so verification, it used to take 20 man-year or person-year years to verify 10,000 lines of code. Today, it roughly takes one man-year to verify the same amount of code. So it's like 20 times faster. But nevertheless, if you want to scale it to the size of 27 millions, it's not really clear how it may work. So verification is fine, and it will be used for some parts of the kernel, right? But it's unlikely that the entire kernel will be within the reach of formal verification. You might ask yourself a question, why not to rewrite past parts of the kernel in a safe programming language like Rust? And in fact, today we have a frameworks which allow us to write parts of the kernel, of the Linux kernel, in Rust. So it's called Rust for Linux. And specifically, you are able to write device drivers in Rust, and the safety and high-level construct of the language allow you to eliminate 70% of CVEs, right? And that's great, right? So it's hard to argue that that's a bad approach, right? But nevertheless, again, like same kind of logic. You can rewrite some part of the kernel in Rust. You can try to use automatic tools. And there is like even a DARPA program which asks the researchers and commercial companies to come up with those tools, to essentially the tools which convert unsafe C code into Rust automatically, right? To make sure that we can take 27 million lines of code and recompile it and run it in Rust, hopefully, hoping that some fraction of vulnerabilities will disappear. But again, it's not really clear if it's possible right now. And what it leaves us with is this idea that maybe you can combine those techniques. So maybe you can combine something like formal verification with something as what we with some flavor of isolation in the kernel, which means that you may be able to verify small parts of the kernel, which are shared across multiple isolated subsystems, and nevertheless you will just take and use old legacy code, ideally with minimal modifications, within those isolated compartments. And if attacker takes over one compartment, it's much harder to essentially attack the rest of the system, right? So it kind of makes sense. So in this isolated system where you run parts of the kernel in isolated, strongly isolated domains, if an attacker finds an exploit, for example, in the TCP/IP subsystem, it's very hard to attack other subsystems. It's not impossible. So, and we've seen that those isolation frameworks can be attacked, but it requires careful stitching of multiple exploits in multiple subsystems. For example, like in this case, to get to the disk to make sure that you can persist an exploit and it will be active after the reboot. So isolation was used in the past. So for example, like Chrome and I think Mozilla as well are using process-based isolation to make sure that individual browser tabs are used in isolation. And my example that yes, those systems can be attacked, but for example, Google Chrome exploits typically require multiple steps. So like maybe this is an example from a pound to own competition, which requires 9 steps and 6 different vulnerabilities stitched together to essentially escape from the Google Chrome environment, which is obviously significantly much more effort heavy for the attacker, right? So, well, that's believable. So if you have piles of essentially old code, the idea is that you're going to be running them in some kind of isolated environments and essentially escaping from one bug into another is much more non-trivial. And you can probably even make sure that you verify small parts of the isolation framework. So for example, maybe if the subsystem talks to something like a memory allocator outside, there is a good belief that memory allocator can be verified, but essentially like claiming that all kernel subsystem will be like within the reach of verification is still kind of naive at this point, but maybe it will change in the future. Okay, what makes isolation hard? So essentially, like again, so there are 2 conceptual challenges. One is performance and second, semantic complexity. So semantic complexity, and I will talk a little bit more about it. Where is it? I just talk about performance somehow. Okay, let's talk about semantic complexity. So essentially, the modern code, like the modern kernels, like FreeBSD, Windows, to some degree Mac OS, although it's more modular, but essentially Linux itself, are not designed for any some kind of a compartmentalized part. I cannot say it. Yeah, for isolation, right? So essentially, this is an example of a graph in the Linux kernel, which it's a strongly connected graph, which was roughly 453,000 nodes. And if you say, look, I want to cut part of this graph, right? So do something like this. Imagine that you have to handle each of those edges somehow to make sure that this isolated component works with the rest of the system. Again, totally non-trivial how to do it, right? And we're going to talk more about it, but intuitively, it seems hard, right? And the second challenge is performance, right? So essentially, remember that we talked about it for the last 2 weeks. So if you simply blindly take page table based isolation, even the fastest like inter-process communication mechanism, IPC, in a CL4 microkernel gives you only the latency of 814 cycles to essentially invoke a function foo across an isolation boundary and then get a result back. And I was also mentioning this number before, but it takes roughly 2,000 cycles to send a network packet in Linux. Essentially, if you add 814 cycles to these 2,000 cycles, your performance kind of like drops by quite a bit, right? And if you work with even faster systems like data plane development kit, DPDK, those spend only roughly 100 cycles per packet. So isolating those is even harder. And nevertheless, like my attempt in the last 2 weeks was to convince you that maybe this new isolation primitives, which we discussed last week, will make it possible, right? So for decades, it was very, very hard or almost impossible to isolate anything without introducing significant performance overheads. But now maybe we're approaching the time when CPU designers will come up with some kind of a primitive, like, I don't know, maybe something similar to Cherry Morella but with revocation, or maybe when we'll to some degree, rewriting the code in Rust is also isolation because, you know, like you encapsulating those attacks in a safe language and like 70% of attacks will be suppressed by that, right? So the question, like, likely in the future, the belief is that those two problems will, and like performance and semantic complexity, will be solved. And essentially, my own work with my students in this field essentially kind of makes a step forward. So, however, just to make sure that we understand that there was a significant amount of prior work. Remember, I aimed at isolating subsystems in the kernel, right? I was mentioning this final report from the Mautic operating system in which the authors claim that, okay, isolation itself is a good idea. It will improve security and reliability of the system. And then over the years, a bunch of teams were trying to use different techniques for isolation of the code, right? So today we're going to talk about two mechanisms, two isolation mechanisms. One is software fault isolation, essentially a compiler pass, which allows you to control each memory access, and hardware-based isolation, like built around one of the existing hardware isolation mechanisms. But you can also imagine different techniques like using language-based isolation, like in this J-kernel, which uses Java, or Singularity, which uses Zing Sharp, or my own work on Redley, which uses Rust, right? So essentially, isolation is not new. And like people tried it, and it was still impractical for many, many years. But the moment you figure out how to solve these two problems, essentially performance and semantic complexity. Semantic complexity of tearing the code apart, kind of like taking like irregular boundary and essentially somehow making sure that it can run in isolation. Then you will be able to introduce isolation in a kernel. Okay, so how does it work? So imagine we have a Linux kernel, and it like usually is implemented in this layered fashion. In this case, we have 3 layers. At the bottom, we have a block layer, which like essentially will use a device driver to write to the disk. In the middle, we have ext3. It's a file system level layer. And on top of it is like a virtual file system. So essentially some generalization, a layer which abstracts details of individual file systems. Typically in a kernel, everything is very, very simple. So if you have a function like write inode, you pass a pointer from BFS into ext3, a pointer which points to essentially an inode. That's how the systems are programmed, right? And essentially everything what is reachable through those pointers like is passed across as well, just because why not, right? It's just a pointer dereference. And so when you essentially submit a BIO, which essentially takes a pointer to a block device, like by the fact that you pass the inode and inode has a pointer to block device, BIO can have this pointer, right? Now imagine if you want to run this in isolation. So I don't know, any level, like essentially, maybe you want to make a cut here. The main question is, how do you pass those data structures across, right? Because intuitively, you might think, okay, if there is a pointer back to some state in the kernel, this some state should not be passed down, right? Also, the state has to be available only temporarily, because only for the lifetime of this invocation, right? Because the moment this invocation is over, intuitively you think that block layer should lose the access to the block device, right? And maybe gain it again in the future when the next invocation is done, but not right away, right? Okay, so the first approach which we're gonna look at today is something what is called LXFI. It's work by a team from MIT. So essentially a group of researchers from MIT, and essentially they use software fault isolation. So like we talked about it. So it's a compiler pass which inserts, roughly speaking, it enforces control flow throughout the program and inserts a bounce checks in front of every memory access, right? So that seems like a good fit for isolation, because the way LXFI works is the following. So, for example, if the kernel wants to pass a data structure, in this example, it's SK path into the driver, which accesses this data structure. Like, for example, here it sees this as an SKB and wants to access this as a field. Like, for example, if it accesses the head field, essentially what LXFI is doing, it inserts some kind of a capability access control scheme in front of every memory access. In practice, like when you do a move instruction, essentially imagine that this is some kind of behind the EAX pointer. They will first do a check. They remember I talked about it. So they do 2 checks. So first of all, they say, look, this device driver will have its own private heap. And so essentially, when the device driver tries to access something, they say, look, you can access your entire private heap. So it's a simple check. So there is like some kind of a bounce from A to B, right? So if this AX is inside the bounds from A to B, access is allowed, right? And if the first check fails, then they do a second check. They say, okay, if you have a capability to access the object behind EAX, and in this specific case, what they do is that essentially they implement some kind of a hash table here. And they look up and essentially say, okay, yes, it looks like that you have a pointer which leads back to this head field, which means that yes, you are allowed to access this field, right? And this move access is essentially passes the checks and it is allowed in the system, right? So why do they split it into two different checks? Just because it's faster, because those capability checks are quite expensive, right? So because you really have to look up the hash table, so they're non-trivial. And so what they're trying to do is that they first say, okay, like if you are in bounds and you're lucky and you can access the heap, and majority of accesses go to the private heap, then you're just lucky and it will let you. And the very first check will pass and you will go ahead and access the object on a heap. If not, a slightly more expensive check will be performed. Okay, seems good, right? So the question is like, what is the problem with this, right? So meaning, like, first of all, performance. So despite the fact that it feels intuitively reasonably slow, in practice, LXFI can kind of match performance of a non-isolated system. So the stock here. So for example, on a TCP stream, an isolated network device driver in LXFI delivers almost the same throughput, right? However, first of all, if we look very carefully in the original system, this TCP workload introduced only 13% overhead. And inside LXFI, it introduces a much higher CPU overhead, meaning that CPU can actually, like CPU does way more computations for those checks, right? And for as long as you still don't run out of the CPU power, essentially, if you have capacity to do more computations, you will be able to almost match the throughput of the original system. However, on the workloads in which LXFI essentially hits the limits of the CPU, essentially here, look, original workload was roughly using half of the CPU. With LXFI, it uses the 100. At this point, the speed of the system will essentially go down just because there will be no extra CPU time to do those additional checks, right? So despite the fact that like the lesson learned here is that even if on the surface, it looks that it's possible to implement isolation without significant penalty in terms of performance, in practice, there is significant penalty because it's hidden inside this CPU overhead. And if you run some additional user code, which takes away your like CPU cycles, then again, you will be penalized. So, which means that, okay, LXFI is a nice approach, but like still a little bit tricky to do fast, right? So maybe it can be done faster with newer isolation mechanisms, something like Intel MPK can be done faster, it can improve performance of LXFI, or maybe you can do something like ARM memory tagging extensions, which we like discussed last time, or maybe even something like Cherry is a good candidate to essentially pass capabilities back and forth. If only you can solve the revocation problem, right? But nevertheless, and the second problem is essentially complexity of those annotations. So essentially in LXFI, every time you pass something across, right? So for example, here in this function probe, which is a function of a PCI driver interface, you're passing a pointer to PCI def, PCI device, right? And you need to pass a capability across. Essentially, you say, look, you will hear that's in their annotation language. They say, look, you will create a reference to PCI def structure and pass it across, right? For the duration of this function call. And actually, there is a conditional check. You might want to revoke it or take it back if return is not zero, is negative. So it's if error happens. But if error doesn't happen, you permanently, I think, transfer those rights to the isolated driver, right? So imagine how hard it is to write those annotations by hand, right? So again, the paper somewhat plays the game of convincing you that it's reasonably easy. And of course, you need to publish, so you have to convince the reviewers that it's actually doable. But in practice, the claim, remember my kind of well-connected graph, is that it's very hard to get those annotations right? And essentially, this is the second problem. This is the semantic complexity of decomposition. Essentially, you say, look, you very carefully have to designate on each function invocation, like if you invoke a function foo, you have to pass those pointers, and those transfer of rights have to be reflected in this C space, in the capability space, so the function itself can access those objects later. So the question is like, is it possible to kind of build a better system which improves both performance and kind of addresses this semantic complexity of decomposition? And this is exactly what we're going to talk now. So these two systems, LXDs and LVDs, LXD stands for lightweight execution domains, and LVDs stands for lightweight VM-func domains, is my own work along with my students, which essentially tries to solve both the problems, specifically these two, try to solve the problem of performance, and then the latest system, which is called K-split, which we're going to discuss today as well, solves the semantic complexity of decomposition. So let's see how it works in this LXDs and LVDs. So back to this figure in which we essentially were passing the pointers across isolation boundaries, right? So every time you cross an isolation boundary in LXDs, you essentially say, look, this C space will be updated. I'm sorry, so specifically point to this one, right? And LXFI would also like include that some kind of support for following the pointers recursively and make sure that other data structures are also passed along. And so when you essentially trying to pass a pointer to a block device here, right, you can essentially update the C space of this system to make sure that it has rights to access this object, right? In my work, which uses hardware-based isolation, we take a different approach. Again, our work is not novel. So this idea existed, and systems like, for example, nukes were using exactly this idea. Essentially, the idea is following. Each isolated subsystem will run its own copy of the heap. Essentially, here we say, look, ext file system will have a copy of the data structure which exists in a non-isolated kernel. Imagine, like in this example, VFS runs within the kernel, and we have two isolated subsystems, ext3 and block layer, right? And the block layer will have a copy of a block device, but ext3 and the VFS will have the copy of all this hierarchy, inode files, superblock and block device, right? Okay, so then what happens on cross subsystem invocations? Because obviously we say, look, what if this state was updated here, right? So because some code in the main kernel updated the state of those data structure, this state has to be synchronized. Essentially, every time we call a function across, we make sure that we have some kind of a TCB which runs in between, which synchronizes this state, kind of like say, look, send and make sure that you update this data structure. And at some point, it looks a little crazy because you say, look, is it really possible to update all the data structures recursively, right? But it is. And with enough automation, actually, it's kind of requires only some minimal human involvement. So, okay, so this work, lightweight capability domains or lightweight execution domains, cuts the Linux into isolated subsystems, which essentially execute like this code, like file system, disk driver. We actually only can isolate device drivers, but for generality, I throw like the rest of the kernel as well. And the main target here is to use unmodified code. So essentially, the goal is to make sure that we have enough plumbing to allow existing Linux kernel code to run in isolation with only minimal changes, which means that we will introduce some kind of a layer. Remember, I said there will be a layer of TCB, trusted computing base, which will run all this isolated subsystem. subsystems. And this layer sits kind of on a boundary between the isolated world and the kernel itself. And we also implement something what we call glue code. So essentially, this blue glue code essentially is responsible for synchronizing state on cross-subsystem invocations. And also this glue code is generated automatically. Otherwise, like in LXFI, we'll have to like manually write those annotations saying, okay, part of the data structure has to be like synchronized across, right? And what we're actually doing here is, let me just erase all the linking on a slide. We use an interface definition language, or IDL, and an interface definition language compiler to generate this glue code. LXFI does something similar, although their interface definition language is probably similar to a macro system, which essentially expands those annotations into the capability updates. In our case, synchronization is more involved, and we essentially have a separate language, separate compiler, which generate this glue code, which then kind of wraps unmodified code of the device driver and allows the kernel to communicate with the isolated driver and back without any changes, right? So let's take a look how it actually works. And everything is also controlled with some kind of a capability interface, but it's really hidden underneath. Essentially similar to LXFI, in this system, the capabilities are just pointers. If I pass you a pointer, you typically have access to the entire object. It may happen that I will block you and will not pass I can pass only a subset of pointers, meaning that if you have 2 pointers in a data structure, only recursively, I only will allow you to follow pointer A, but not pointer B, because otherwise you're going to reach the state of the entire kernel, right? So this is how it works at a slightly more lower level of detail. So here we have a kernel code, which invokes this function register net def, and the driver code, which runs in isolation. And it's essentially just okay, actually the invocation goes the other way. So it's the driver invokes the register net def in the kernel, right? And what it does, it passes this data structure, net device. So as I was saying, the system will run 2 copies of this object hierarchy. So both the driver and the kernel will have its own copy of struct net device, and we will be synchronizing those on cross subsystem invocations, right? And this synchronization will be done with the glue code. So essentially in practice, when the driver code, unmodified driver code, performs invocation of register driver, it doesn't immediately land on a kernel. Instead, we compile the kernel in such a manner that it lands on a glue code trampoline, which is responsible for marshalling parameters, meaning sending the state of those data structures across and essentially updating the fields of those data structure, and then performing essentially a cross subsystem invocation, kind of like saving the registers, switching the stack or whatever we have to switch, and essentially then upon return unmarshalling arguments, making sure that the fields which are updated by the kernel will be reflected inside the driver, and then returning a result and returning from the invocation, right? At a high level, kind of doesn't look very hard. The challenge, however, is to make sure that it works with a ton of low-level kernel idioms. Essentially, the kernel itself is developed in C. It's reasonably carefully crafted C, but still it's low-level C, right? And you do all sorts of things. Like, for example, here, this SKB data structure, which is passed inside the between the kernel and the network device, has a pointer to the data region of the SKB, where the actual payload sits. And a bunch of other pointers point within this data region. So the head itself points to the beginning, the data points in the middle, because this is essentially the beginning of the payload, and this is actually the packet headers. There is also some numerical fields like tail and end, which count essentially the end of the payload and the end of the data region itself. And then at the end of the data region itself, there is also a list of fragments, because this SKB itself may not be represented as a single data region, but instead like have multiple additional fragments. And you essentially will have something like a list of those to make sure that you can kind of do a scatter, gather, send. The question is like how to synchronize those data structures across the isolation boundary. Okay, just to give you an illustration of this semantic complexity. So this SKB data structure has 66 fields, right? So it's not trivial. It's not very small. It's not the biggest, but still it's not the smallest. It has 5 pointers, right? So you have to be careful because you have to choose how to deal with those recursive pointers, because it might require like synchronization of recursive data structure. And recursively, if you follow all the pointers, you will have 3,132 fields in different data structure reachable through those pointers, reachable from the SKB above, and 1,214 of those will be pointers, right? So that's kind of like imagine you're working with something like Cherry, for example. So, and you say, look, I will just use Cherry, and like every pointer will be a capability. So you still have to be very, very careful in all these systems like Cherry, my own LXDs, which we're discussing like right now, and LXFI, which we discussed like earlier in the lecture. You still have to be very, very careful with how you deal with recursive pointers, right? So not trivial, right? In practice, however, only a very small subset of these fields is accessed by each invocation, right? So if you invoke this IXGB XSmith frame, so only 8 fields of this data structure are synchronized across. So we essentially we have to distinguish the private fields, which are essentially never synchronized across the isolation boundary. Maybe they're private to the kernel, maybe they're private to the driver, to the isolated driver, or maybe they're shared, used interchangeably by kernel and the driver, right? So essentially, you have to come up with a language which defines those relationships. And so we came up with this interface definition language, which essentially describe which fields of the data structure have to be synchronized across. So here, for this data structure, the first argument def, we actually might enumerate some field, or we might leave it empty and just say, look, this is actually a pointer. You can kind of refer to this data structure, but you cannot access a single field. Or maybe inside the SKB, you can access 2 fields, data, a pointer to data, and a pointer to len. And we also make sure that like when we don't have like an in or out specifier here, this field is synchronized both ways, from the driver to the kernel and on the way back from the kernel to the driver, because it can be updated by both the kernel and the driver. And so if you essentially take a look at a specific IDL example for this function, NDO_XSmith, which transmits network packets. So like some fields like this len are synchronized in and out. This is only synchronized one way in the in direction, and we don't have a single one which synchronized only on out. But essentially, you see how it works. So this keyword projection means that we will project some selected fields of the data structures into the other subsystem. And essentially, that's how we defined what has to be projected. And here for the net device, I don't think we synchronize anything. So because this projection is empty, but maybe it's just an example. Okay, cool. So this language allows us to synchronize individual fields of data structures across the isolation boundary. It significantly simplifies the human effort. And as we see, we have a couple of implementation of the isolation boundary. So this first paper, LXDs, uses 2 different cores. So essentially, instead of executing on a single core, we run the isolated driver on one core and the kernel on another core, and we send cross-coherent messages across, right? Like 10 years ago, arguably that was the fastest method to synchronize, to perform those cross-subsystem invocations. And those invocations were reasonably fast. So here we have a performance graph for the TX outgoing bandwidth of the isolated driver compared to the native driver red and isolated blue. And the blue driver kind of roughly isolated driver stays within like 12% of performance. So it's not bad, right? So and this is the growing number of threads. It's not ideal. It's not like zero performance overhead, but still it's reasonable, right? However, the second isolation boundary, which we developed, was addressing the issues with this LXD system. Here, when we essentially run threads on two different cores and essentially perform those invocations and back, it becomes an asynchronous system. So really, we built an asynchronous runtime for the kernel. So you could have written something like async and like say execute function foo and execute function bar. And essentially the async will kind of say, look, I will execute foo, but I'm not going to wait for the completion of foo. I will go ahead and execute bar at the same time. And maybe like here, when you kind of like have a finished primitive, I will wait for both functions, which I dispatched asynchronously to finish. So, but that was introducing some obscure bugs because you really like take synchronous code and in order to optimize performance, rewrite it in this asynchronous manner. That was kind of like not the best idea. Especially also there was some kind of like nonsensical corner cases where you allocate a spin lock on one core and essentially kind of synchronize the state with the driver, but then this driver like essentially sends the like completion on another core. Then you need to introduce an additional locking here to make sure that those data structures are coherent. So it's hard to understand what I mean, but okay, it wasn't fun and it wasn't super fast. That's why we built the second isolation boundary. So structured around extended page table switching. So this extended page table switching or VM func mechanism, so it's VM functions, allows you to create a nested page table and switch between them reasonably fast, right? So it was available in like probably 2015, but we built a paper in 2020. So essentially what here we were doing is that I didn't explain this isolation mechanism earlier, right? So it's a brand new one. So we talked about Intel MPK. So Intel VM func is kind of a similar mechanism, but built around the extended page table. So essentially it allows you to run two virtual machines. So essentially the whole kernel executes as a virtual machine on top of a minimal hypervisor. And the isolated device driver also runs as a virtual machine. So essentially in VTX non-root on top of this hypervisor. And essentially to perform a cross-subsystem invocation, we switch the extended page table. Remember, extended page table maps guest physical to host physical memory, right? So essentially, if you have two EPTs, EPT1 and EPT2, extended page table 2, then by switching between them from like 1 to 0, you change the view of memory. And essentially, suddenly parts of your address space become inaccessible because they're not mapped by the EPTs, right? So essentially, maybe like this half was accessible to the kernel, and this half becomes accessible to the isolated driver. In practice, there is like a ton of non-trivial attacks, and supposedly this work patches most of them, or at least we make a convincing argument that we know how to deal with them. So that's fine, and it's actually faster, and it's also synchronous because it's one thread of execution. T1 just essentially jumps through a small trampoline into the isolated driver, but it's the same thread. We do, of course, switch the stacks, right? So kind of very, very similar to Intel MPK, which we discussed before, but slightly different, right? With more corner cases. So, okay, cool. So I talk about the architecture, but maybe it like doesn't really matter. So this is the overlapping EPTs. So EPT of the kernel is this kind of lighter green. EPT of the isolated driver is kind of like darker green. and this area is overlapping, and this is where the trampoline will sit. So essentially, when you send a message across, you can invoke VMFunc. VMFunc immediately jumps here, and on the way back, you will be jumping backwards. And you're sitting on top of a tiny rootkit-like hypervisor, which we built, which essentially, when the kernel boots, it just sticks itself under the kernel, kind of virtualizing or deprivileging the kernel into the EPT kernel. And then when the drivers are loaded, they will be loaded in the EPT isolated, like on their own different EPT page tables, right? So it turned out that this one was faster. So TX bandwidth now, like you cannot even like nearly distinguish the native from isolated, right? So it's like roughly speaking 2 to 5% overhead on a collection of like system benchmarks. So it was a step forward, right? However, so we kind of remember I said in those systems where you introduce isolation, there are two main problems: performance and semantic complexity. So these LXDs and LBDs, they do solve the performance problem somewhat. There's a little bit of cheating in those papers, as you say. If you really care about the performance, you will find a workload which will be unfairly penalized with frequent cross-domain switches, right? So maybe like, again, VMFunc itself might have something like 450 cycles for the IPC invocation. That's better than 840, but it's still not zero, far from zero again. So there is a little bit of like, for some workloads, it doesn't matter. So like for those like workloads which send network packets, you can hardly see the difference. If you send more network packets, or maybe if you go to 100 Gbps BPS device drivers, and we're testing on a 10 Gbps device driver, maybe it kind of like hurts you a lot more. So be careful with that. We kind of solved the performance, but I'm not saying that we solved it completely. But we made a step forward, and hopefully the CPU designers will come back with even better isolation mechanisms and make sure that even like those overheads even become even lower. But what's interesting is that on a journey to build this system, we came up with a solution to solve the semantic complexity problem. Essentially, we came up with a system which uses static analysis for generating those ideal files. Because in LXDs and LBDs, we roll those ideal files by hand. But K-split is a static analysis framework, which essentially writes the glue, like the interface definition language, which then generates the glue code nearly without the human intervention. And that's kind of a great result, because this this allows you to automate isolation or decomposition in the kernel to the degree that human is almost not involved. And at this point, we're going to be just waiting for the faster isolation mechanism. The moment it arrives, arguably K-split plus that mechanism enables practical isolation in the kernel, which significantly also like raises the bar for the attack. Okay, so let's take a look. So remember my example for the network buffer, writing this manual specification for the interface definition language was hard. And so K-split is a static analysis, which essentially addresses this complexity. And the complexity, just to illustrate it, is like, again, the driver, IXGB driver, it's a network driver, uses 134 functions on the kernel. The kernel itself uses 81 functions of the driver, but they pass a ton of different objects across. And they use various low-level programming idioms, like they use pointers, they use singletons and arrays, and like array in C looks like a pointer, right, at the level of the API, so you cannot distinguish it. So you need to somehow know that it's an array. They pass linked lists, they collocate data structures, meaning sometimes they have a data structure A, and they know that B was collocated exactly next to A. So essentially, when they were doing malloc, they set size of A plus B, and then they do something like A1 to essentially just shift the pointer from A0 to A1, exactly here, that's an ampersand, and address B, and typecast it into B. They use sized and sentinel, and array sentinel means that it has 0 at the end, and that's essentially marks the end, kind of like strings. They use some special pointers, like some of them point to IO memory and have to be treated differently. Some are user pointers, which are coming from the user address space. The most painful idiom is tagged unions. Essentially, you say, look, it's a union type, and one field encodes which type are we using right now. That helps you to implement polymorphism in C, but it's extremely painful to marshal. They sometimes return, they use upper bits of a pointer to say that it's really an error, not a pointer, because they know that the pointer cannot exist in the address space, and it just signifies that the function which returns a pointer instead returns you an error, right? So you have to be careful. And essentially, like, you also have to carefully reason about concurrency primitives, meaning that, you know, if you have a spin lock and you essentially acquiring it and like changing some state, you actually have to make sure that you synchronize the state by the time you unlock the spin lock, right? Otherwise, you know, the other isolated subsystem doesn't see the most recent state. We have to distinguish between pointers and arrays. So essentially, the question is this point to a singleton, meaning it's just one instant of SKP, or it actually points to the array of SKPs, right? And maybe the second field size will tell us how many elements on this array. So you have to be careful with this static analysis to make sure that, you know, you can distinguish singletons from pointers. But nevertheless, those problems were solved. And the way we did it is that we, let me show you. We built a static analysis engine, which takes the source code of the kernel and constructs something what is called a program dependency graph. So I will show it in a second. Then we essentially use this graph to perform the analysis on the data structures and essentially identify the subset of fields which are used on both sides of the isolation boundary. And after that, we essentially we reason about those shared fields and essentially say how they are passed across some function invocations and how they are used in atomic regions, kind of like under spin locks and other synchronization primitives, and generate appropriate interface definition language for each shared field, right? That allows us to kind of automate decomposition. And this program dependence graph essentially is a way to scale static analysis, or more specifically, even alias analysis. It represents the kernel as a graph, and essentially just then later, essentially you can collect information about individual fields within the function, like VFS read, or instead of MSR read. And essentially when this field is, the data structure is passed across, you can stitch them in a graph, making sure that you can reason about the kernel globally, right? So this technique allows us to essentially scale the static analysis to the size of the kernel. And the original paper is done by my co-authors, who essentially, like, it's called a PTR split, right? Which advocates for these techniques as the way to scale the static analysis. And so essentially that's pretty cool. So in practice, K-split solved a range of problems. Essentially, it addressed semantic complexity of decomposition. So granted, it's not fully automatic. So the kernel developer, sometimes IDL has to be patched. So static analysis says, okay, I really cannot distinguish this alias. Are you pointing to this data structure or that data structure? So they don't really know. And so what happens at this point is that the kernel developer goes and manually writes the IDL. But still, in case of IXGB, there was some small number of lines of code which have to be patched. The majority of the IDL was correctly generated by the K-split static analysis engine. However, having done all of it, so we learn how to efficiently isolate kernel subsystems, and we know how to do it automatically with this static analysis engine. The main question, which we still have today, is that did we really solve the problem of security? Meaning, imagine you're running something in isolation. This is, imagine IXGB, our lovely example, right? And okay, it invokes the kernel across the isolation boundary. This is the kernel. I can invoke some function foo here. Foo does something on a kernel state, and then maybe returns. The question, does it give you any practical security benefits or not? And it would be nice to discuss it in class, right, live. But the unfortunate problem, which we started understanding towards the end of this project, is the security benefits are very, very minimal. The problem is the complexity of this boundary. Meaning, remember, the kernel was developed in a shared address space. This boundary involves like lots of different constructions which pass the data structures by reference. They assume that you follow a specific, oh man, no, still running. Yeah, hold on, sorry, I was thinking that I actually lost connection to my Wacom tablet. That you follow a specific protocol. So for example, you first probe the driver, then you open the driver, then you do read and write functions. And what happens if you're trying to do read and write before opening the driver? Maybe the kernel crashes because it assumes that you have to do it, like the kernel trusts the driver, right? And it turns out that it's very easy to construct an exploit. If you already control execution inside the isolated subsystem, you can construct an attack on the kernel, which we call a cross-interface vulnerability, meaning that we cannot access the memory of the kernel directly, right? That's off bounds. So like we have this isolation boundary here, but we can do something funky with the kernel to confuse it and essentially find a bug in the kernel itself. I'll give you just a couple of examples just to make sure that we can carry this argument forward. So we discussed this possibility of those attacks in this follow-up paper, which kind of says that there is probably a possibility to evolve the kernel towards secure kernel driver interface, but we don't really like know how to do it yet. So just a couple of those attacks. So in this specific example, the attacker can trigger an out-of-bound access in the kernel. Why is that? Because here, the attacker has write access to the page offset field inside the driver. If attacker already controls the driver, it can update it to some large value, right? And the IDL doesn't capture it because it's a scalar field. So it's like, it doesn't know that this page offset will be used for something else. And then later the kernel uses this to essentially like in a function which does something like a memory copy. So obviously like, okay, we didn't access the memory of the kernel directly. We just updated this field, but this field is used in a function, which is mem copy function. And so this overrides memory of a kernel within the kernel, right? Despite the fact that these two pieces of code are isolated. So that's just one attack. And you can quickly start thinking that you can invent like numerous example of those attacks if you like stir this, if you look at this isolated interface for long enough, right? Here's another example. SKB, for example, assumes that one SKB points to one data region. But what happens if attacker says, okay, two different SKBs, which I will synchronize back to the kernel, will point to the same data region? Well, kind of like doing this assignment within the isolated driver. What happens when the kernel first frees the first SKB, recursively frees the data? Obviously, that's how the destructor in the kernel works. And then you use the second SKB because this is no longer live memory. So this was deallocated. So it's a use after free attack because we just confused the kernel that, you know, the two SKBs point to the same data. You can imagine an attack in which a linked list, for example, has a loop, right? Why not? If you synchronize the linked list, like the IDL has to check that there are no loops in the linked list, right? And then the kernel will be looping forever, trying to like reach the end of the linked list, something like that. Same attacks, like very practical with lifetimes. So for example, sometimes the drivers control lifetimes of objects in the kernel. So for example, this consume SKB function, it's not executed in the driver. It calls into the kernel and like says, okay, look, I'm implementing a ref counter, reference counter on the SKB packet, right? And if the attacker essentially says, well, why not to do it twice? Why not? Because it found a bug in the code in the driver, which loops and decrements the counter twice on the same SKB. Obviously, this SKB gets deallocated, but if the kernel still holds a pointer to this because originally it incremented the counter as well, assuming that the SKB will stay alive for as long as the kernel doesn't decrement the counter. The kernel accesses a deallocated memory, and it's a use for free attack. And if you look at it, you will understand that there are like tons and tons of those attacks. And it's totally non-trivial to make sure that you take an unmodified C code or maybe C++ and turn it into something what it provides some kind of isolation guarantees in terms of security. So, okay, this is where we are. So essentially our own work now is to come up with those like principles for how to construct better isolation boundaries, which can resist those cross-interface vulnerabilities or CIVs, right? And we're trying to essentially derive those principles for how to construct a better kernel in which majority of the code can still be reused, but still run in isolation, and yet those cross-interface vulnerabilities can be addressed. So I should probably stop here. On Wednesday, I will teach on completely different topic on using language-based isolation, and we essentially will cover another kernel, which is called Redleaf, which is an operating system which was implemented from scratch in Rust, which uses Rust for isolation instead of hardware or software fault isolation techniques. So it's yet another technique which we never discussed in this class. So I hope that you will come back and like watch the lecture. Okay, thank you so much. I'll stop here. See you